Hello and welcome to another session in physics. In this session we'll be looking at the topic pressure. We'll also be looking at Archimedes principles of thrust and laws of flotation. But before that, let us review the previous lesson. Welcome back. At this point, let us take the definition of pressure. You see, pressure is defined as the perpendicular force per unit acting on a surface. So we can simply say it is the ratio of force to area. That's pressure. Pressure is a scalar quantity and it is measured in Newton per meter square. Why is it Newton per meter square? Because you know the SI unit of force is Newton and the SI unit of area is meter square. Gives us Newton per meter square. Alternatively, it is also measured in Pascal. Pascal written as PA. Pressure can also be calculated by taking the total force of a body and dividing it by the area over which that force acts. But it's important for you to note that force and pressure, though they are related to each other, they are totally different. The reason for this is because a very small pressure, if it is applied to a large area, it can produce a very large total force and vice versa. So you can see the equations here, force over area, which gives us pressure measured in Pascal, force measured in Newton, and area measured in meter squared. We also have other multiples of pressure, which is 1 bar. Bar is also a unit of pressure. 1 bar is equal to 10 raised to the power 5 Newton per meter squared. We can say 10 raised to the power 5 Pascal. That's 1 bar. So when you hear 1 bar, know that it refers to 10 raised to the power 5 Pascal. Now let's take this example that will help us to apply the principles that we just talked about now. It says that a force of 40 newtons is acting on an area of 5 meters squared. And we are asked to calculate the pressure that has been exerted on the surface of that body. So we know that pressure is given by force over area. The force here is 40 newtons, the area is 5 meters squared. So when you divide both of them, 5 divided 40 is going to give you 8 Pascal or 8 Newton per meter squared. That's the answer to this question. All you just have to do is divide the force by the area and then you get the equivalent of the pressure. Now let's talk about pressure in liquids. Pressure in liquid has the following properties. About 5 of them. The first one is that pressure increases with depth. Pressure increases with depth, which means the deeper you go, the more pressure there is. Also, pressure depends on density, which means density is directly proportional to pressure. More density, the more pressure. The less density, the less pressure as well. Number 3 is that pressure at any point in the liquid acts equally in all directions. You have to understand that liquid is a fluid, so it almost always takes the shape of its container. So at any point in the liquid where there is pressure, it acts equally in all directions. The first is that pressure at all times is at the same level in a liquid. At all times, at all points, pressure within a liquid is simply the same. The 5th point we need to get across is that pressure is independent of cross-sectional area. So pressure has nothing to do with the cross-sectional area. It is independent, it does not depend on the cross-sectional area. Pascal was one scientist that made huge strides in the field of pressure. He talked about what is being known today as Pascal's principle. Now, according to Pascal's principle, it says that the pressure that is applied to an enclosed fluid is transmitted undiminished to every part of the fluid as well as to the walls of the container as well. An example of this was found in the operation of the hydraulic press and the brakes of a car system. The which relies on this principle. So you can see from there here the hydraulic press system, how it works, how it's used to fix a car in mechanics. It says that when there is pressure that has been applied to an enclosed, it affects the walls of the container as well as every part of that fluid as well. Another person that made huge strides when it comes to density and pressure is a man we know as Archimedes. He propounded a principle known as Archimedes' principle. Archimedes' principle is a law that explains the phenomenon of buoyancy and upthrust. Now, Archimedes' principle states that when a body is completely or partially immersed in a fluid, for instance, if this is a bowl of water, let's say this is a bowl of water, and then you have something like a bowl. A bowl is partially or totally immersed inside this fluid here. It's that body experiences what we call an upthrust. It experiences what we call an apparent loss in weight. In other words, it doesn't really weigh as much as it did before it entered into that fluid. And that apparent loss in weight, that weight it looks like it might have lost, is equal to the weight of the fluid that has been displaced by that particular body. According to a story, it was said that Archimedes discovered this law while he was taking his bath. He said that an object experiences an upthrust that is due to the fact that the pressure exerted by the fluid on the lower surface of the body is greater than that exerted on the top surface of that body. Since we all said that pressure increases with depth, so we said pressure is directly proportional to the depth, which means the deeper a body goes submerged, the smaller the pressure, the higher the pressure, but the smaller the depth, in other words, the shallower the depth, the smaller the pressure itself. So pressure increases with depth. The deeper you go, the more the pressure, the more shallower it is, the pressure. Pressure is given by an expression known as this equal to H, this and G. This is P for pressure, like there. H is the height or the depth of the body, and then this is a Greek alphabet called rho. Rho is a Greek alphabet. Rho is written as RHO. It's a Greek alphabet, and then we all know that G is acceleration due to gravity. Acceleration due to gravity, which is given by 10 meters per second squared. Alright, so we want to talk about 2 points that are very important. That when an object is wholly immersed, this object displaces its volume of fluid. So we say that upthrust is equal to the weight of the fluid that it displaces. Think about a bowl that is filled with water. When you put in a ball inside this bowl, because that ball has already been filled up with water, it's going to find it difficult to accommodate this. So for that reason, this ball is going to displace some fluid. The upthrust, the apparent loss of weight that this ball experiences, is equal to the weight of the fluid that the ball displaces. It is also equal to the volume of fluid that has been displaced times its density times acceleration due to gravity, and is also equal to the volume of the object times density of the fluid times acceleration due to gravity. That's the first point of Archimedes' principle. The second point is that when an object is partially immersed, remember we've talked about wholly immersed. Now this is partially immersed in water. For example, let's say 1/4 of its total volume is being immersed. Then the upthrust is given by the volume divided by 4 times the density times acceleration due to gravity. So, talking about these two things, let's see the mathematical expression for the relative density of solid. Relative density of solid, I'm going to write it as RD of solid. It can be given by weight of solid in air, weight of solid in air divided by weight of equal volume in water. Weight of solid in air over weight of equal volume in water. So if we say that the weight of the body in air, weight in air, and that W2 is the weight water, then we can say that the relative density of the solid is going to be given by weight in air over weight of equal volume in water is going to become W1 minus W2. And then for the relative density of the liquid the liquid itself, yes, is going to become RD of liquid, which is equal to apparent loss of weight of the solid in liquid, which is W1 minus W3. W3 is the given liquid itself. We're going to divide it by W1 minus W2. And I've already told you that W1 is weight in air, W2 is the weight in water, and W3 is the given liquid itself. Alright, so these are the two situations we need to be aware of. Now let's take this final example. It says that stone is 15 grams when it is completely immersed in water, and 10 grams when it is completely immersed in a liquid of relative density 2.0. And we're asked to calculate of the liquid in air, mass of the stone rather in air. So for us to find the mass of the stone in air, first of all we need to find relative density. Relative density is going to become up thrust over, of course, up thrust in liquids over up thrust in water. Up thrust in water. Now let's use W to represent the mass of the stone in air. Let W represent mass of the stone in air. So we're going to have 2, which is the relative density, equal to W, which is the mass of the stone in air, minus 10, which is its mass when it is completely immersed in that liquid, divided by mass of the stone in air, which is W, minus 15, which is mass of the stone when it is completely immersed in water. So taking proportion line, we're going to have this equation now, which is going to give us something like this. So 2 times W is 2W, minus 2 times 15 is 30, 2 times 15 is 30, and then W minus 10 here. So at this point all we have to do is collect like terms. So 2W minus W equal to minus 10 plus 30. 2W minus W is W, like 1W, minus 10 plus 30 plus 20 grams, and this is the mass of the stone in air. Now let's talk about the law of flotation. The law of flotation talks about an object its own weight of the fluid in which it floats, or an object that floats when the up thrust that has been exerted on it by the fluid is equal to the weight of the body itself. So we're talking about when an object is floating freely, that is, it is not sinking nor is it moving vertically upwards, then it simply means that the up thrust must be fully supporting the object's weight. It is this principle that ships use today to move on seas and so on and so forth. It helps bodies to float. And that is it for let's take the urge to take as many examples as you can in the material that will be attached to this video. Thank you for joining us in this lesson. To refresh your memory of what we just discussed, please take the text that will appear on your screen.